Okay, so welcome to the lecture covering the fundamental theorem of calculus, part 2. Okay, so this is, I would say, probably the more useful version of the fundamental theorem. So part 1 talked about, remember, part 1 of FTC said d dx of an integral that looks like this is just the function evaluated at this variable, so long as it's of this format. And now part 2 says the following. If f is continuous and differentiable on an interval, I should be more careful here. This is sort of the same thing as mean value theorem. Continuous on the closed interval a to b and differentiable on the open interval a to b. Then we have the following. The integral from a to b, just on any bounds, of the derivative of f of x. So let's just say, let's do this just to keep with the format. With respect to x is, I think I use capital F's actually. Let me change that. Is exactly f of x, but I put brackets around it because I want to write a and b like this. This means that I evaluate f of x on the interval a to b. What does that mean? Well, I use this notation to show that basically derivative and integral are essentially inverse again, right? The integral of the derivative gives me back the input. Just like last week, right? Just reverse the order. But here, just like last time, it's a little subtle. So it's not quite just the function. I have to take the top bound and plug it in, and then subtract what I get when I plug in the bottom bound. So I get f of b minus f of a, right? So this is dependent on the interval that I'm on, right? So it's dependent on this a and b. It's not, completely independent of those. So it's not completely an inverse, but it's pretty close. Now, this is how you should compute integrals from now on. Okay, this is basically the beginning of learning power rule and things like that. So before we had how do I evaluate the integral using the definition, similar to evaluating a derivative by definition. But once we get more powerful tools, we don't have to use the definition every time. We can use sort of shortcuts or these rules that always work. This is going to shed light on how we get new rules for these things and basically how we compute them in the future, right? I should say though, unless we say to evaluate by definition, right? Just like with derivatives, right? It's the same exact process we're going through. Okay. So what do I need to know? Well, let's think about this. If I'm given an interval or an integral like this, interval from 1 to 3 of, let's say, 3x squared dx. Okay, now, the way this is written seems like it's a little different than what I have over here, right? This makes it clear that I've taken a derivative of a function, and that's what my integrand is. That's what the inside of the integral is. Here, though, this is just a function. So I have to rewrite this as the derivative of another function. So we have the question. What function do I take the derivative of let me say it a different way. What function has derivative? Has its derivative equal to 3x squared. Now this might be obvious for some of you, right? You just sort of look at it a little bit and you think, all right, well, how do derivatives work? And the answer is f of x equals x cubed, or I should say, should use capital F here. Usually we use capital F for antiderivative, and that's exactly what this is. This is an antiderivative of 3x squared. Okay. Now, why do I say an antiderivative, right? Not the antiderivative. Remember, when I take a derivative, I can say this is the derivative of the function. But I say this is an antiderivative because here's the second answer. What about this? Well, let's check. The derivative of f of x is the derivative of x cubed plus 1. And remember, derivative is linear, so it applies to each term. So I get 3x squared, just as I planned, plus 0, right? Because the derivative of a constant is 0. So this is 3x squared. So in general, let me put this over on the side. In general, we can say the antiderivative of a function, in this example, f of x equals 3x squared, is x cubed plus c, where c is, I should write the function, sort of changed my mind halfway through that, of the function, where c is a constant, right? So if we're just talking about a general antiderivative, which more on this in the next lecture, we have to remember to add a plus c, because we want it to be as general as possible, right? We want to take into account x cubed plus any constant out here, because if I take a derivative of it, well, I get 0 in that term. So this is just to be as general as possible. However, for this guy, for the fundamental theorem, for any definite integral, this is called a definite integral. That means that there is a definite interval that I'm working on. For any definite integral, all I need, right, definite integral, all I need is a, or an antiderivative. So we can pick any of them. And why is that? Just a quick explanation. Let's continue with the example. You can see it pretty clearly, I think, in this example. What was my interval? I don't remember. 1 to 3. Okay. 1 to 3 of 3x squared dx. Okay, so let's pick the general one, right? So my general antiderivative is going to be, like we decided, x cubed plus c, right? And I evaluate that from 1 to 3. So now I get, all right, I plug in 3. This is 3 cubed plus c, right? Plus c stays. Minus, I plug in 1. 1 cubed plus c. All right, so I get 27 plus c minus, and remember this minus distributes, right? Minus 1 minus c. So the c's cancel. In every case, the c cancels. So I get 26. And it's because of that subtraction. So again, I'm going to emphasize this. When dealing with definite integrals, let c equal 0. Meaning just ignore it, right? Just take what the most sort of obvious answer is. So in this case, x cubed. Now, I sort of waved my hands over the whole finding x cubed thing. So let's try to make a list of rules. And I'll sort of collect them all at the end, but let's think about maybe another example briefly. Because evaluating, once I have this function in here, it's easy, right? I just plug in numbers and subtract, right? That's the easy part. It's finding this thing that really is not too easy. You have to do derivatives backwards. And that's not really intuitive yet. But maybe, you know, after enough examples, we can come up with some sort of rules. Okay, so let's try another one that's sort of similar. So let's do, I don't know, let's say 0 to 1 of, let's say just x dx, right? That's sort of an easy one. Or even, you know what? Maybe even something even easier. Let's do a constant. See what happens. So let's make it 3. Okay. Now, linearity still works with integrals, right? We talked about that. We talked about that last time. With these definite integrals, linearity still works. So just by linearity, I get 3 times the integral from 0 to 1 of 1 dx. Okay, so now we can check ourselves because this is something that we've dealt with, right? I know what this integral is because it's a geometric object. So it's equal to the area of the section underneath the graph. And the function f of x equals 1 is exactly this, just the constant function, right? So it's f of x equals 1. So I just count up this area because I'm living between 0 and 1, because that's what the integral tells me. And of course, this is just a rectangle, or in this case, really a square. So it's 1 times 1. So I should expect that my answer here is 1, which means that I get 3 times 1. So I should expect my answer to be 3. So I should expect a 3 out here. And let's make sure that we do everything right. Okay. So whose function, what function has derivative equal to 1? All right, that's sort of an easy one. Looks like x, right? I just apply power rule, bring the 1 down, and drop this. That kills off the x, and I have a 1. Okay, so it looks like this is 3. Of course, I have to carry the 3 through. Actually, I should be more careful here. The way I have it written, I should say 3 times x. It doesn't end up mattering, but I should be careful. And I evaluate x on 0 to 1. Okay, so I have 3 times the interval, or times the value of x when I plug in 1, I get 1, minus the value of x when I plug in 0. So I get 3 times 1 equals 3. Okay, so let's try another example. Let's try something similar to what we had before, 3x squared, and I'll even keep it on the same interval. Integral from 1 to 3 of, let's say, just x squared dx. Okay, so how do we figure this out? Well, last time we said, all right, well, the 3's here, so it looks like it came from the power, right? And then I dropped the power by 1. Okay, so it looks like, basically it looks like a power rule. And I just have to reverse what that was. Well, here it's not quite as obvious, right? But there's sort of a trick that might make it a little bit more obvious. And this isn't a trick that you'll have to have memorized or anything. This is just sort of a way to see the rule before I write it out, because I don't want to just write it and, have you memorize it. I would rather you sort of understand what's going on. So notice that there definitely is a 1 here as a coefficient. But I would like there to be a 3, right? If there was a 3 there, then I know exactly what that derivative is, right? Because I just figured it out. Right? It's just a power rule and I have to reverse it. So notice that 1 is the same thing as 1/3 times 3. And I'm just rewriting 1. Okay. So I have 1/3 times 3, which is just 1, times x. So I've just rewritten what I had. I can have this equals here. Everything's fine. All right. Now just regrouping, because multiplication is associative, I can put the parentheses wherever I want. This is 1/3 times 3x squared. Okay, and I can pull the 1/3 out. And I know what this integral is. Or at least I know what his antiderivative is. This is 1/3 times x cubed from 1 to 3. So I just take whatever answer I had before, 26, and I multiply them by 1/3. 26 over 30. Okay, so it looks like if I didn't do this trick here, I could just take this antiderivative by taking my f of x equals x squared and adding 1 to the power, right? I get an x cubed here. And then I get a 1/3 here. So it looks like I just divide by 2 plus 1. So if I do that process, I get x cubed over 3. It turns out this works in general. Oh, sorry, I clicked. In general. Rule 1 will be that the integral from a to b of x to the p dx is equal to x to the p plus 1 over p plus 1. And then I evaluate him from a to b. All right, so this is just a general antiderivative that I've picked, namely when c equals 0, right? If I take a general one, I'd have to have plus c. And I evaluate him on a to b. And this is how I compute anything of this form. And of course, this extends because if I have a constant here, say some k, I can just pull him outside. and he comes along for the ride. So there's no real difference in the computation that I do. And this makes sense, right? Because if I have the derivative with respect to x of x to the p plus 1 over p plus 1, so this is just to check, to make sure that I've actually taken the proper antiderivative. Well, remember, p plus 1 is just a number. So this is really d dx of 1 over p plus 1 times x to the p plus 1. And if I apply power rule, I bring the p plus 1 down, multiplied by 1 over p plus 1 gives me 1, and I drop the power by 1. So I get p plus 1 times 1 over p plus 1 times x to the p plus 1 minus 1, or just x to the p. And that works. Okay, so there's my first rule. There's my first shortcut rule. This is sort of the reverse power rule. Right? You're just doing the rule in reverse. It's as simple as that. One thing, however, to notice about this is that this rule only works when p is not equal to -1, right? I mean, this should be sort of obvious for one reason, just because if I take the derivative, or I take the antiderivative this way, then I get a p plus 1 on the bottom, I would be dividing by 0. And that's a big no-no, regardless of what stupid things I write in the homework. But when p equals -1 is an interesting question. So what about when p equals -1, right? Now we don't have an answer for that. We don't know what the rule is. So let's take a look. Let's go, I don't know, from 1 to 4 this time is fine. And we'll do the integral of x to the -1 with respect to x. Okay, so I'm going to rewrite this so it's a little bit easier to look at. This is 1 over x. Okay, now the question. Whose derivative is equal to 1 over x? The answer is ln of x, right? If I take the derivative of ln of x, this is just one of the things I have memorized, right? 1 over x. However, there's one thing that I have to take into account. In this case, it's not that big of a deal because I have only positive values here. But if x were allowed to be negative values, and in the case of a general antiderivative, it certainly is, x could be anything, then I have to make sure that this function makes sense, right? Because I can't take the ln of a negative. So how do I fix this? I fix it by writing absolute value. Okay, so in general, I have this. Well, in this example, I have ln of absolute value of x from 1 to 4. So just evaluating, I get ln of 4 minus ln of 1. And the absolute value didn't affect this in any case, or in this case, but, and then I can simplify because ln of 1 is 0. I get ln of 4. Okay, so in general, rule 2 is that the integral from a to b of 1 over x dx is ln of the absolute value of x from a to b. Okay. And of course, this extends linearly, right? If I had something like this, I can't have 0 because I can't take the ln of 0. I'm not going to make that mistake. 1 to 2, let's say. If I had, say, 3 over x or something, right? Of course, this is the same thing as 3 times the integral from 1 to 2 of 1 over x dx. So I get 3 times ln absolute value of x from 1 to 2, and I get 3 ln of 2, because ln of 1 is, again, 0. Get this, right? So these examples, there's not much flavor I can really throw at you. If you see a 1 over x or a number over x, you know it's going to be an ln as its antiderivative or as its integral. How about some trig functions, right? We know what the derivatives of the trig functions are, so we should be able to figure this out, right? So let's do the integral 0 to pi over 2 of sine of x dx. Okay? Let's make it easier. Let's make it cosine. Slightly easier. Cosine of x dx. Okay, so the question is, again, whose derivative is equal to cosine of x? And the answer should be pretty easy. Is sine of x, right? Derivative of sine is cosine, right? That's just something we have memorized, right? The proof is a little complicated. Okay, so I just get sine of x on the interval 0 to pi over 2, and I evaluate. What's sine of pi over 2 minus sine of 0? Sine of pi over 2 is 1, and sine of 0 is 0, so I get 1. Great. Okay, so how about a similar example, but instead this time we do what I wanted to do originally. Sine of x. Okay, so new question. Whose derivative is equal to sine of x? Okay, a little more subtle this time, because remember that the derivative of cosine is equal to negative sine, right? So how do I fix this? Multiply both sides by a negative. So the antiderivative of sine is negative cosine. Okay, so I get negative cosine of x evaluated from 0 to pi over 2, pi over 2. Negative cosine of pi over 2 is 0, and then I get a minus negative cosine of 0, so I get minus 0 minus a negative 1, so I get 1 in this case as well. Okay, so in general, we have rules 3 and 4. I guess I'll just call them 3a and 3b. Probably make more sense. So rule 3a, rules, look at me, can't spell. Rule 3a is that the integral from a to b of the sine of, and I'm going to call this, I don't know, what do you want to call it? Kx dx. Actually, what do I use in the notes? Because I'll try to keep that consistent. I guess I use a there, which is stupid. So I'll use something like alpha x. So I have alpha x, sine of alpha x, where alpha is a constant. Alpha is just a Greek a, and you just read it as like a k or a c or any other letter. It's just a constant. Right? This is equal to cosine, negative cosine of alpha x, right? Just like we saw before. But to account for this alpha in here, you divide by it. So how do we make sense of this? Well, let's check. The derivative with respect to x of the negative cosine of alpha x over alpha. Okay. So remember that the derivative of negative cosine is sine. That makes sense, right? So I get definitely sine of alpha x, and I get this 1 over alpha on the outside as well. That sort of comes along. I get my sine of alpha x, but remember that I have a chain rule in here, and I have to multiply by the derivative of the inside. And the derivative of the inside in this case is alpha. So I get just sine of alpha x. And that checks out. Okay, similarly, I do exactly the same thing for this. And I just get sine of alpha x over alpha. So these are my next 2 rules, and these are the ones that deal with trig functions. And I guess we could also do another one that sort of comes along. Oh, I'm sorry, these should be evaluated on these intervals. I keep forgetting that. We could do secant squared of alpha x dx, right? Because I know whose derivative equals secant squared, and it's tangent. So I similarly get tangent of alpha x over alpha from A to B. Okay, so I have rule 3, A, B, and C covering the standard trig functions. Now, just in terms of remembering things, here's how I remember derivatives and integrals of sine and cosine. And this really is pretty nonsensical, so if it doesn't, help you at all, then that sort of makes sense. But I imagine sort of a list that repeats itself. So I imagine I have sine, cosine, then negative sine, then negative cosine. Okay? And I remember that for this list, I list them out. So sine we usually introduce first. I think of sine as sort of first in the order, and then cosine is second. Then you just repeat that with negatives out front. Now, to go down the list, you're taking derivatives. And to go up the list, you're taking integrals. So I sort of have this picture in my mind. And when I think, all right, what's the derivative of sine? I just have this picture, and then I take a step down. Now you might ask, what happens when I take the derivative of negative cosine? Well, it loops. So you sort of loop back up to the top. And then similarly, what's the integral of sine? You loop back down to the bottom, right? So derivative of sine is cosine, derivative of cosine is negative sine, integral of negative sine is cosine, integral of cosine is sine. So you can sort of walk up and down this list in loops as you're doing these computations. That's how I think of it. If it's helpful, fine. If not, then that's fine too. Okay, so I think there's one more. Yeah, there's one more rule that we need to build up, and then I'll list them all out all at the end. So let's look at, say, the integral from, I'll just keep doing 0 to 1. I think that's fine. Of e to the x dx. All right, now I would say this is probably the easiest one. Who has derivative equal to e to the x? And of course the answer is, well, just e to the x, right? This is a nice function, so this integral is e to the x evaluated from 0 to 1. So I get e to the 1 minus e to the 0, which is e minus 1. Okay. All right, now what about if I had something like this, same bounds again, e to the 2x? Well, what about that? Who has derivative equal to e to the 2x? Well, it's the same sort of principle that we've been using, right? Normally, when you take a derivative of this, you take the same function, and then you divide, or then, I'm sorry, yeah, I just gave it away. And then you multiply by the derivative of the exponent. In this case, you take the antiderivative, which is you just write it again, and then divide by the derivative of the exponent. So it's e to the 2x over 2. Let's check. The derivative with respect to x of e to the 2x, I guess that's just times 1/2, sort of ran out of space there, is e to the 2x, right? I just take this and I write it the same way, just by chain rule, and then I multiply by the derivative of the inside, which is 2, or of the exponent, and then I still have my 1/2. This 1/2, this division by 2, helps us sort of cancel out because we've predicted the chain rule. So the 2 and the 1/2 cancel, and I'm left with just e to the 2x. And that checks out. So this is e to the 2x over 2 from 0 to 1. So this is e over 2 minus 1/2. All right, so a general rule, rule 4, is that the integral from a to b of e to the alpha x, I'll use the same notation again, alpha constant, is e to the alpha x over alpha, evaluated on a to b. Okay. So let's have a big collection of rules. Rule 1 was the reverse power rule. This is the one that said the integral from a to b of x to the p dx is equal to x to the p plus 1 over p plus 1 evaluated on a to b when p is not equal to -1. Rule 2 is when p is equal to -1, what do we do? Well, when p is equal to -1, I have 1 over x dx. And we have ln of the absolute value of x. Now, the absolute value is very easy to forget, so make sure you pay attention to that from a to b. All right. Rule 3. Remember, there are 3 parts here. Part A is the integral from a to b of sine, I think it is sine first, sine of alpha x dx is negative cosine of alpha x over alpha from a to b. B, integral from a to b of cosine of alpha x dx is sine of alpha x over alpha from a to b. And C, integral from a to b of secant squared of alpha x dx equals tangent of alpha x over alpha from a to b. Okay, and finally, rule number 4 is the integral from a to b of e to the alpha x dx is simply e to the alpha x over alpha evaluated from a to b. This is the list of common rules. This is sort of our, derivative rules that we came up with. And I think we came up with basically the same ones when we dealt with derivatives for the first time. Maybe we had a few more, but it turns out integration is a little bit harder. So you may be asking yourself, well, what about something of this form? Integral from 0 to 1, I'll just keep 0 to 1 as my bounds in this case, of x squared times e to the x dx. Well, what about this? Remember, the derivative of a product is not the product of the derivatives. Right? Remember, we needed a product rule. And the same is true here. So integration and derivatives work basically hand in hand in that if it's not something you can easily take a derivative of, meaning if it's not like an obvious derivative, it's probably not an obvious integral either. So this is not equal to dx times integral from 0 to 1 e to the x dx. This is not equal to this, right? There is a more complicated way to solve this sort of a thing. It turns out that pretty much the only way you can do this, unless you get lucky with this sort of substitution, sometimes u sub what I mean by that is u substitution works if you're lucky. And you'll see this method next week. And this will be the last sort of thing that we do in the class. In most cases, though, you need integration by parts. And I'll just say C Calc 2 at Lehigh. That's where this technique is taught. And it's a pain. Everybody hates it. And it's horrible. It's even worse than like the quotient rule or the product rule. It's extremely annoying. So it's probably a little bit beyond us in the class. Plus, we're getting down toward the end here. So that's just sort of a warning. To not fall into that trap. Of course, we won't ask you a question like this if you can't solve it, but don't just think that it splits up into a product like this. That's definitely a big no-no. And then one last thing to make sure of before I end this lecture. It's important to make sure the integrand is a continuous function. on the given interval, a to b, right? When you're looking at the integral from a to b of f of x dx, right? I need to make sure that this is continuous. So just one example of this is the following. Let's look at the interval from -2 to 1, and we'll take the integral of the function 1 over x squared dx. Now, let's take a look at what the graph looks like to get an idea of what my answer should be. Looks something like this, and like this. This should be symmetric, but I can't draw. And there's an asymptote right here, right? Okay, so remember, I'm looking to calculate area under this curve, so it's going to be all of this down in here. So it looks like, it's a little deceiving because it looks like it might be infinite, but there is actually a chance that this is finite. Now, that's something we won't get into in this class, but one thing is for sure, that this should be positive. Right, because if I cut off at, say, -2 and 1, right, if I'm only looking at this area in here, I mean, if I'm looking at the area of the whole thing, it's definitely positive, but certainly on this interval, this should be a positive thing because it's all above the x-axis. So let's see, and let's try to apply the fundamental theorem. So this is really just x to the -2, and because this exponent is not equal to -1, I can apply the reverse power rule, right? So rule number 1. So I add 1 to the power, and then I divide by the new power that I got. I get x to the -1 over -1. I go from -2 to 1. So this is really just -1 over x from -2 to 1. And I get -1 over 1 minus, and then I plug in a -2 to this. So I get a 1/2, and the negative here from the -2, and this negative that came along with the antiderivative are going to cancel. So I get a -1/2. -3/2 here, which is less than 0. And that's no good, right? And it was because I have this asymptote going right through the middle of my interval. Now I can take the integral of this thing on an interval from 1 to something else. That's totally fine. Or -2 to something else, right? If both of my bounds are both positive or both negative, then it's fine. It's as soon as I cross over 0 in my interval that I have an issue because it's not continuous on the whole thing. So that's just one thing to keep track of in something like this. That saying that the function needs to be continuous and differentiable means something. It's definitely necessary. So FTC doesn't apply, meaning it doesn't work, right? You can't use it. Okay. If there are any questions on this lecture, feel free to stop by office hours or send me an email. And I appreciate you listening.